And we are on round three. Um, third FRQ. Usually, third FRQs in any sort of AP Physics C exam are challenging problems. This one, just looking at the setup, you might think, I don't know, this little thing swings down, hits a ball. How hard could this be? The average score for this was about 3.2 points. I don't remember what the standard deviation was. Maybe it was another like 5 or something. Like the people scored negative. So this is a hard one. We're gonna do some of the setup. I'll let you know that I have gone through. I have solved this whole problem. It's not pretty. It's the type of thing where this is the question where you get to go, nope, I'm going to use the 10 minutes I got banked from this one, and I'm going to use it to solve problem 1 or 2 to get some more points out of them. But anyways, let's take a look at it and see if we can figure out some of the problem. All right, so it says a system consists of a small sphere of mass m and radius r, there it is, on a horizontal surface and a uniform rod of mass m, capital M equals little m times 2, and length L, all right, it's up there, attached to one end of the pivot with negligible friction, where r is much smaller than L. There is negligible friction between the surface and the sphere to the right of point A. That would be here. So there's no friction there. And non-negligible friction to the left of point A. The rod is held horizontally as shown in figure 1 and is released from rest. The total rotational inertia of the rod about its pivot is this. The rotational inertia, that's the correct formula, about the sphere about its center is that. After the rod is released, the rod swings down and strikes the sphere head on. As a result of this collision, the rod is stopped. So it swings down, hits it, the rod stops, and the ball moves. The ball initially slides without rotating because there's no friction. So no friction means it won't roll. It'll just slide. And then it says determine an expression for the angular speed of the rod just before striking the sphere in terms of the length L and the physical constants. Okay, so this is kind of a tricky one. If I've got the rod here and it's going to swing down, it's going to receive a torque, and that torque is going to be acting at its center of mass. It's going to have a clockwise torque. The weight force is there, but the issue is once it starts rotating down, that torque is going to change angles. And so whenever we have something that's moving from a big height to a smaller height and it's changing angles and stuff like that, conservation energy is the way to go. The catch here is that the conservation of energy we're going to have to use is the gravitational potential energy of the stick turning into rotational kinetic energy. So gravitational potential energy turns into K rotational. And setting that up for part A could get you some credit, but it'd be better if you were to elaborate on that and say that the gravitational potential energy would be m times g times the height that it's released from, which is, it's released from height L, but when it swings down, that's about to make this wrong. When it swings down, the center of mass only gets to here. So it's only dropping down L over 2. Ooh, it's a catch right there. So it's L over 2 is the height that it has to drop. And then for the rotational kinetic energy, it'd be 1/2 I, which is 1/3 mL squared times the omega squared that it'll have, right? We want the angular speed of it. So that's a setup, and as I'm looking at it, I'm also realizing, well, m is 2m, so I really got to put that in and simplify it, but you know what? That's when we got more time. Look at this. I'm already down to just over a minute and a half. That's ridiculous. Part B, derive an expression for the linear speed v sub 0 of the sphere immediately after colliding with the rod in terms of L and physical constants as appropriate. So this is a collision, and here on our one-pager thing, said as a mass collides with something that can rotate, you treat the mass as if it is a part of a rotating system. So here, if I wanted to set this up just to get some credit, I could say that L initial is equal to L final, conservation of angular momentum. I could just write that as a statement. But I would have to say that it's going to be the I for the rod multiplied by the omega that it has from up above. and this is a sphere, but it's not rotating. When it gets hit, it's just going to slide. So we treat this, it's not something hitting a stick, it's a stick hitting a thing. So in this case, I would just treat it as a point mass particle. I'd use the MVR. So I could say that the mass of the sphere, I'll just put it as an S, times its velocity, they're calling it V sub 0, multiplied by the radius that it's acted on, but that's the radius from the pivot, which would equal L, right? Yeah, it would equal L, because that's how far it is from the point of the pivot here. And I could set that up and I could find a solution. I have to put in what the I is and everything like that. Look at that, 5 minutes is already up. Okay, it says after sliding a short distance at time equals 0, the sphere encounters a region of horizontal surface with the coefficient of kinetic friction mu, beginning at point A as indicated in figure 1. The sphere begins rotating while sliding. Oh, so it's sliding and rotating. It's like a bowling ball. And eventually begins rolling without sliding at point B. So that's the common way of looking at it. We'll see if we can get a couple more things set up here. We're not going to finish this problem. We're not even going to get to the end of it, I don't think. So let's see. As indicated in the following diagram, which represents the sphere while it's traveling between A and B, draw label forces, not components. All right, well, this is easy. This should be like a couple of points right here. Free body diagram. Now, it's difficult when they say pointing away from the point of application of the sphere. Instead of drawing a dot, they actually have it as a two-dimensional shape, so you really have to be careful where you draw stuff. The weight force should be right here, drawn from the center of mass, but the normal force would get drawn upward, and those should be the same size. I apologize, that one looks a little longer. And then the friction force would be at the bottom. So some friction force acting on the bottom of the sphere there as it slides. It's sliding while rolling, so it's going. Let's just read parts D and E. Is that all there is? There is. Okay. See if there's something I can write down to eke out a point. Because if I do this and this, I think I got more than 3 points already, to be honest. And I've only spent 7-ish minutes working on this. So part D, derive an expression for each of the following spheres rotating and sliding between points A and B in terms of those things. The linear velocity V is the center of the center mass of the sphere as its as a function of time. So it's sliding and rolling. So, I mean, it's going to be sliding. So it's got kinetic friction acting on it. They want to know the velocity as a function of time. The easiest thing to do here would be to say that V is equal to V0 plus AT, and then get an acceleration in terms of those other things, mu and R and T and whatnot. You could say that acceleration is equal to the net force over, the only force along the direction of motion is the friction force. So it'd be friction over mass, and then try something there. The angular velocity omega of the sphere as a function of time t, I would say that you're probably going to want to do this. But in this case, you're going to want to get alpha as torque over I, and then move from there. That might be worth a point or so. I'm not going to do the rest of it right now. I like to keep these videos 10 minutes or under, so we got about a minute left here. Derive an expression for the time it takes the sphere to travel from point A to point B in terms of V naught. So the catch from point A to point, we don't know how big that is. Don't know that. What does the other one say? Derive an expression for the linear velocity of the sphere upon reaching point B. 20 seconds to think about this one. I would just say no. No, I'm not going to do that. You can't make me. But the person inside who's already read the problem knows that the catch here is that when it gets to point B, it's no longer sliding. So that means that it's going to be at a constant angular velocity at that point. It's gotten its maximum amount. And that's kind of the catch for setting this one up. But we'll have to take a look at that another time. This video is concluded. I think we've scraped out some points on this, probably more than the average. So good for us. Anyways, I'll see you in another video.